Hello and welcome. In today's video, we are going to be integrating MSP430 G2553 Launchpad and the DHT11 sensor. By the end of the video, you'll be able to get the temperature and humidity data from the DHT11 sensor to the Launchpad. So let's get started. Let's see the outline for today's video. First, we are going to be having an overview of the DHT11 sensor and its pins and connections. Then we'll speak about its communication process. After that, we are going to be giving a short description of the MSP430 modules like digital input and output, basic clock control, and timer capture compare modules. After that, we are going to be creating an algorithm for the application. And by the end of the video, we are going to be creating the C code in Code Composer Studio. Let's have an overview of the DHT11 sensor. DHT11 is a digital temperature and humidity sensor. It has 4 pins. First pin is the power supply pin. Second pin is the serial data pin. Third pin has no connections, it's empty. And the fourth pin will be connected to the ground. Once you properly initiate the DHT11 by the microcontroller, it sends the temperature and humidity values in 40 bits as follows. First 8 bits is going to be the humidity integer part. Second byte is going to be the fractional part of the humidity. Third byte is going to be the integer part of the temperature. Fourth byte is going to be the fractional part of the temperature. And lastly, we are going to be having a byte as the checksum. In our code, we are going to have to add these 4 values for humidity and temperature and compare it with the checksum. If the 2 values match with each other, it means that we received correct data. Let's see the pins and connections for our application. First pin is going to be directly connected to VCC. Second pin is going to be connected to a pull-up resistor of 10 kilo ohms and then to the VCC. And it will have a direct connection to the microcontroller's 2.4 pin. Third pin is going to have no connections and fourth pin is going to be connected to the ground. In this slide, we can see the diagram and also the picture of the connections. As you can see, we have a 5-volt connection to the resistor. And from the same node, we have a jumper cable connected to pin 1 of the DHT11 sensor. The data pin of the DHT11 sensor is connected to P2.4 of the microcontroller. And we have a ground connection from the fourth pin of the DHT11. Let's see the communication process for DHT11. DHT11 uses a single bus communication. Its second pin, data pin, will be connected to microcontroller's P2.4 in our example. At this point, you can ask yourself, how are we going to use the same pin for transmit and receive operations? We'll see it in the slide. DHT11 uses a 4-step communication process. At step 1, after power up, no connection should be initiated by the microcontroller towards the DHT11 for at least 1 second. Because the sensor will be in an unsteady state at that time. On second step, the microcontroller's port, in our example it's P2.4, which is set up as an output port, should stay low at 0 level for at least 18 milliseconds and then switch to high. On step 3, the port is going to be switching from high to low. At that point, we should set it as an input port, because DHT11 is going to be sending data. At that moment, DHT11 is going to be sending 80 microseconds of low and 80 microseconds of high, meaning that it's starting to send the data. And on the last step, DHT11 is going to be sending the 40 bits of data like this. For sending a 0 bit, it's going to send 50 microseconds low and 26 to 28 microseconds high. And for sending a 1 bit, it's going to send 50 microseconds low and 70 microseconds high. In the next slide, we are going to be seeing the details of this communication process. On the left hand side, we have our microcontroller, and on the right hand side, we have our DHT11 sensor. Let's see the communication steps in detail. In first step, we are going to be having a delay of at least 1 second after powering up the DHT11. In the second step, our microcontroller is going to send at least 18 milliseconds of low and then it's going to switch to high. You can see in this graph that we have around 1.8 times 10 to the power of 4 microseconds of low, and then a comparatively shorter period of high. On the third step, as the microcontroller switches from high to low, DHT11 is going to send 80 microseconds of low and 80 microseconds of high. Please be careful that we have different scales in these two graphs. Here we have 80 microseconds of low and 80 microseconds of high. And in the last step, as we already know from the previous slide, DHT11 is going to start to send 40 bits of data according to the timings mentioned earlier. So let's see how it's done. As you can see, in the first frame, we have around 50 microseconds of low and 26 to 28 microseconds of high. We know that this is a 0 bit. Our second frame is similar to the first frame. This is also a 0 bit. On the third frame, however, we see that we have 50 microseconds of low and around 70 microseconds of high, which corresponds to 1 bit. On the fourth frame is similar to the third frame, which is also a 1. Fifth frame has 50 microseconds of low and around 28 microseconds of high. So this means that this is a 0 bit. And it goes on like this until DHT11 sends the whole 40 bits of data. Now let's speak a bit about the MSP430's modules, registers, and commands that we used in our setup. First module is the digital I/O. In digital I/O, we use several register commands like pxdir. This one is used for setting up a pin as either input or output. pxout register is used for setting an output pin as either high or low. And the third one that we are using is the pxl and pxl2 registers. These are used for changing the purpose of the pin. Initially, they are both set as 0 and that corresponds to digital I/O. However, if you select pxl as 1 and pxl2 as 0, then the selected pin is going to be used as timer and clock. In basic clock control, we are using two commands in our setup. These are used to set the DCO, digitally controlled oscillator, and BCS basic clock system, master clock and submain clock to 1 MHz. And in the third module, which is timer and capture compare module, we will be using two commands. First one is going to be selecting the submain clock as clock source, and it's going to select continuous mode for the timer. The second command is going to set the timer to capture mode. It will enable the capture compare interrupts. Capture input select to P2.4. It's going to set the capture mode as falling edge, and it's going to synchronize the capture signal with the clock. Before we start to write our C code in Code Composer Studio, let's see the algorithm for it. First, we are going to be doing the declarations. In this one, we'll be including the header files and defining the global variables. And then we'll start with the main function. In the beginning of the main function, we are going to be stopping the watchdog timer, which is done automatically by the Code Composer Studio. And then we are going to be setting the DCO and SM clock to 1 MHz. Next step is going to be the first step of our communication process, which is a delay for at least 1 second. Then we are going to start with the step 2 of the communication process, and we will set port 2.4 as output, and we are going to set it to low. Next step is going to be giving a delay of at least 18 milliseconds, and then we are going to set the port 2.4 to high. So this will be the completion of the step 2. For step 3, we are going to be delaying for n microseconds. Actually, we'll be using 20 microseconds in our code, and then we are going to set port 2.4 to low. For the step 4, we are going to set up P2.4 as input and timer because we would like to get the data from the DHT11 sensor. And then we are going to configure the timer registers. And after that, we will be enabling the general interrupts. After enabling the general interrupts, we are going to see whether we captured the whole 40 bits of data coming from the DHT11 sensor. And if that's okay, we are going to filling in the variables for humidity and temperature by organizing the capture data. Since we will be obtaining the data from the DHT11 sensor by using interrupts, we need an ISR, interrupt service routine. This ISR will say that with each capture, we are going to write the capture times to an array of 40 elements. We will see how it's done in Code Composer Studio. So let's go ahead and open Code Composer Studio to write our code. Before we start to write our C code in CCS, I can say that it's possible to skip this part and use the link that I provided in the video description. There you'll be able to find the exact code that we'll be writing now. However, I strongly suggest that you follow the coding process in CCS in order to fully understand how we are reading the sensor values. After learning this code, you'll have the opportunity to enhance it. For example, you'll be able to use it for multiple sensors, obtain the values periodically, or send the obtained values to some other microcontroller unit. Besides, you'll also be familiar with concepts such as capture interrupts, delay functions, and bitwise operations. Let's start by creating a new C project. And let's call it, for example, DHT11 demo. Be sure that you choose empty project in main C and click finish. There you go. We have our main.c in the editor window. We can clear these comments. As you can see, once we create the project in our main.c file, Code Composer Studio directly includes the MSP430 header file automatically. This is because I had identified MSP430 family during the setup of the CCS. Now let's go through the steps that we identified in the algorithm. I'll be defining some global variables that we will be using in our code. We will use these two arrays for capturing the data from the sensor. So this one is not for temperature but temporary, and we will use this one for differences. Actually here an array of 41 elements is sufficient. However, I'd like you to see where the process stops. This diff array is going to be used for getting the timestamp differences between capture times. This is one of the indices that we are going to use. Let's create another one. And call it J. This one is going to be for the humidity high byte. We will have another one for the low byte. We'll have for the temperature high. We'll have one for temperature low. We'll get the capture checksum from DH11 and assign it to this variable. We will add the 4 bytes that we received from the DH11 sensor for temperature and humidity and assign it to this variable. And we'll set this data OK variable to 1 if check and checksum values are the same. Let's get rid of this return 0 by defining our main function as void. As you can see, CCS automatically stops the watchdog timer. Right now in our main function, we'll be going through the steps that we had already identified in our presentation. So let's start by setting the clock. And also digitally controlled oscillator. Okay, now we need to have a delay of at least 1 second. So let's make it 2 seconds for being safe in the demo. Here we use the delay cycle intrinsic function. In parentheses, we should specify the number of cycles for the delay. Since we are running the device at 1 MHz, each cycle is going to be 1 microsecond. So here we have to write 2 million. Now we should set the P2.4 pin as output. Here, bit 4 corresponds to a hexadecimal number. Actually, it corresponds to hexadecimal 10, 10. So this means that if you do an OR operation for the P2D register, you will set bit 4 as 1. Remember, port numbers are between 0 and 7. Since we set P2.4 as output, initially we should set it to low, 0, by using this command. And now we need to wait for at least 18 milliseconds. So let's make it 20 milliseconds. For 20 milliseconds, I'll have to write 20,000. After 20 milliseconds, we should set the port to high. And after that, it's sufficient to wait for 20 microseconds at the high level. Then we should set the port as an input port. And also we should set it as timer and clock. Okay, now we'll use the two commands that we had mentioned in the presentation. First one is going to be using SM clock as input source, and it's going to select continuous mode for the timer. I'll try to provide separate videos for MSP modules. However, I can provide a short description on the continuous mode. In continuous mode, the microcontroller unit starts to count from 0 to 65,535 since it uses a 16-bit time register. So we can say that we'll have a period of 65,535 microseconds, and during this period, we'll get the timestamps for the capture times. This second line sets the timer to capture mode so that we can get the timestamps for the data received from DHT11. It enables interrupts so that we can perform some calculations in each interrupt. Sets the falling edge as the capture mode. This may be the most important part of the process, so let's discuss this in detail. Let's see the step 4 once again. As you can see in step 4, we'll receive 40 plus 1 for the initial frame, as you can see here, of 80 microsecond low and 80 microsecond high from the sensor. In order to record this data into variables, the most convenient way is to use the falling edge capturing. By using the timestamps of the falling edge, we can define whether the received data is a 0 or a 1. For example, after the first frame, this one, which is supposed to be 160 seconds, we will get a falling edge interrupt at either 160 plus 78, which is equal to 238 microseconds, or 160 plus 120, which is equal to 280 microseconds. And similarly for the other coming frames as well. So by each falling edge, we'll be able to calculate whether the bit is 0 or 1. Let's continue to our code. We have a small typo here. Let's correct it. After entering the timer commands, we need to enable general interrupts with this following command. Okay, we've entered our timer commands and we enabled the interrupts. Let's create an infinite loop by while one command. At this moment, we are not going to write any code in this one. Let's write down our ISR first. Before defining the ISR, we should write down our interrupt vector with the following command. This identifies the memory address of the piece of code for our ISR. Now we can write down our ISR. We can call it timer A1 or anything we would like to, or anything we want. Okay, now in each capture, we would like to assign a timestamp to our temp array. We can do it with this command. So whenever we receive an interrupt, we are going to copy the TACCR2 registers value to the temp array. And then we should give an increment to I. Even though we need to keep the ISR short, we can fill in our diff array at this point as well with the following command. As you can see, by this command, we can get the differences between two falling edges and assign it to our diff array. Lastly, in the ISR, we should clear the interrupt flag. We should clear the interrupt flag in order to get new interrupts. Okay, this was the end of the ISR. At this point, we can run our code in order to see if we get the values to our temp array and diff array. And then we can continue to fill in our variables for humidity and temperature. Let's save our code and let's debug it. Okay, there are no errors. And the code is now ready to be run on the microcontroller unit. When we click on this resume button, it can run on it. However, first let's add our temp and diff arrays in the expressions window since they are global variables. And once we click on resume and then suspend our code, we will be able to see the content of these arrays. Let's click on resume. We need to wait for at least 2 seconds because you can remember that we've already identified the 2 seconds of delay in the beginning of the code. Now let's click on suspend. Okay. As you can see, we have obtained some values in our arrays. In our temp array, we have, if we scroll down, we have 41 values. The index of the first element in the temp array is 0. So we have here actually 41 values. The first value is corresponding to the initial frame that the DHT11 is sending. You can recall that it was sending 80 microseconds low and 80 microseconds high. We were expecting around 160 microseconds here, but we have less. There is a reason for this. Actually, as you can see, we had set the P2.4's direction with this command, and then we have identified it as timer and clock. And then we have written 2 different lines of code where, for example, we set the submain clock, capture, compare, interrupt, enable, and etc. So while executing these commands, we are already losing some microprocessor cycles. So that's why we are not able to see 160 here, because DHT11 has already started to send the data. But for the other ones, we will be able to get the correct timings. So if we look at the diff array, we will be able to see it. Our initial element has 0 value because in the interrupt we had started from while I is equal to or greater than 2. So now our initial value, as you can see, is 78 microseconds, which is directly corresponding to bit 0. Second one, again, 78 microseconds, which is bit 0. However, third one is equal to 124, which is definitely a bit 1. We were expecting 120 microseconds here, but it can change due to the characteristic of the DHT11 sensor that we are using. So we know that this is a bit 1. This one, again, a bit 1, bit 0, bit 1, and etc. And it goes on like this. It continues. And the last byte, as you can remember, is the checksum. So now that we have the values in our temp and diff arrays, we can construct our humidity and temperature values by writing some code in the while loop. So let's stop our code and continue filling in the while loop. First, we need to check whether we received whole 40 captures or not. So in order to do this, we are going to write if I is greater than or equal to 40, then as you know, we are expecting 5 bytes of data: humidity high, humidity low, temperature high, temperature low, and checksum. So we are going to create 5 different for statements in order to fill in these variables. I'm going to write starting from J, starting from 1, less than or equal to 8 with an increment. I need to define a threshold in order to distinguish between bit 1 and bit 0. For example, I can set it to 110 microseconds. You can say 100 microseconds as well, but I think 110 microseconds is okay. If the value is greater than this, we are going to have bit 1. If it's less than 110, it's going to be bit 0. So we are going to write if j value is greater than 111, then this might be the tricky part, but I will explain it to you. Okay, here, since we are dealing with the humidity high value, what we are doing here is shifting one bit according to the index if we have a value greater than 110. If diff1 is greater than 110, we are going to shift one bit to the left 7 times, okay? So it's going to create the most significant bit of the humidity high as 1. And it's going to continue doing this for the whole humidity high value. We are going to continue to do it for the other values as well. Let's copy this one. Let's make it tidier. Okay, now we need to change the starting from 9 to 16. The value that we have is humidity low, and we'll have to shift our index value to 16 so that we fill in the value correctly. Okay, we paste once again. This is going to be temperature high starting from 17 to 24, and this one is again 24. This one is going to be temperature low starting from 25 to 32. Again, we have here 32. And the last one for checksum, it's going to start from 33 ending in 40. This one will again be 40, and this will be checksum. Let's save it. Okay, now if everything works fine, we're going to obtain 5 bytes. Okay, now we can check whether received the correct data or not. So what we'll do is, we had already defined the check variable. It's going to be humidity high plus humidity low plus temperature high plus temperature low. And we can say that if this value is equal to the checksum that we received, then we can set the data OK variable as 1. Otherwise, data OK variable is going to be 0. Okay, let's check if the parentheses are okay. Yes, while loop, and this one is for the main function. It looks okay. Let's click on save and let's debug our code. We have some errors. Let's see what they are. Okay. We were expecting some semicolons, correct. We forgot those. Let's write them down. Yes, and this one as well. These are okay. Let's again click on save. Let's debug once again. Great. We don't have any errors now. Okay, great. Now we can add the other variables like humidity high, humidity low, temperature high, temperature low. We can add checksum. Let's add check and then checksum and whether we received the correct data. Again, let's click on resume. Let's wait for at least 2 seconds and then we can click on suspend. Okay, great. It seems that we've filled in some data. As you can see, humidity high is 55. This is in percent. We don't have a, let's say, fractional part for it. Our temperature is 27 Celsius and temperature low is 2. So this is 27.2 Celsius. Great that we have the same values for check and checksum. This means that our data is okay. So since we did not include most of our code in the while loop, we will not be able to click on resume again, suspend again to get the, let's say, updated values. We can do it just in order to see it by yourself. Let's click on resume. If we click on suspend, actually nothing is happening at the moment. We are going to get the same values. As you can see, no value is highlighted in the expressions window. This means that all values are the same as the previous values. In order to check it once again, I'm going to stop. I'm going to debug once again. Proceed. And let's click on resume again. After 2 seconds, let's suspend. Okay, there you go. Now we have 56. It was, I guess, 55 before. 27.2 temperature is the same. Check and checksum values have changed, obviously, because we have an updated humidity high value and our data is okay. So as you can see, we were able to obtain the data from the DHT11 sensor. It took a bit long because we didn't have any libraries to include. We have written the code from scratch. We have done bitwise operations, bitwise shift operations. We've done everything by ourselves. So that's why it took a bit long time. But after this, you can enhance the code so you can use it for other purposes. You can use multiple sensors. You can periodically check their values. You can also send these values to, for example, 4-digit 7-segment displays or other displays, so you can display them. You can send it to another microcontroller unit, or you can send it to, let's say, a Raspberry Pi. You can evaluate these values there as well. So this was the end of the video. I hope you enjoyed it. In this video, we were able to integrate the DHT11 with the MSP430 microcontroller. We did the coding from scratch. We didn't include any libraries. Hope to see you in another video. Bye.